All right, so this lesson on optimization is actually something we did look at a bit earlier in the course before we learned about calculus. But we're going to more depth here, and in general, optimization problems are one of the more sort of classical applications of differential calculus. There's an incredible variety of types of questions, and since we do have access to graphing technology, many times you don't actually need to differentiate anything. Depends on what you're asked, but clearly I'll take a focus of differentiating here. And so let's look at a problem. And like I mentioned before, there's a huge variety of possible problems. Here it says there's 40 apples in an orchard. Each tree produces 600 apples in a year. For each additional tree planted in the orchard, the output of each tree drops by 10 apples. So the idea being, as you plant more, you have more trees, but they crowd each other, and so potentially they get a little less productive. That said, how many more trees should be planted to maximize the total production of apples? And in general, optimization problems tend to have some sort of goal like this where we want to maximize or minimize something. Depends if it's, in this case, we want to maximize the number of apples. And other times, if it's a cost, quite often we want to minimize the cost. That's it. Let's think about how many apples we can produce. I'll say P for the production of apples. Right now, it's 40 apple trees times 600 apples each. But we want to imagine we can add more trees. We can plant more trees. So I'll say plus X. So 40 plus X. This represents the number of trees we have. And each tree produces 600 apples, but for every extra tree we add, they actually goes down. It goes down by 10 for each tree. So 600 minus 10 times X, that represents the number of apples per tree. And so notice when X is 0, if we don't plant anything extra, it's just 40 times 600. And so as we plant more trees, we have more apples being produced, but at some point when we plant too many, they'll crowd each other out so much that it'll actually become counterproductive. So I want to maximize this. Now, one option, if the wording of this question doesn't state anything about derivatives, we could just graph this, and I will get to that. However, quite often on assessments, on tests, they'll break it down, and at some point we need to think about the derivative. So let me first just expand and simplify this. If I multiply this out, I get 24,000 minus 400x plus 600x minus 10x squared. Just distributing everything out, collect like terms, and I get 24,000 plus 200x minus 10x squared. So I have a quadratic function. And that is my function of how many apples I produced, where x is the number of trees we're planting. All right, if I want to find the maximum number of apples we can produce, I first want to differentiate this. So I'll find the derivative of p, which in this case is 200 minus 20x, just using the power rule a couple of times. And if I want to find, the reason the derivative is helpful is if I can make my derivative equal to 0, then I can find either a maximum or a minimum of this function. And so I have a very simple derivative here. If I make it equal 0, I get 20x equals 200, which means x equals 10. And that's my only time, there's only one solution to this. Which means here, if I plant 10 more trees, we should maximize our number of apples. And so, well, that's my answer, right? 10 more trees, keep in mind. So we should have a total of 50 trees. Keep in mind, in terms of just the question, as soon as I had this done, I could solve the question by graphing. So I do want to also jump to that. So I'm going to graph this, and I have it in Desmos here. Now I need to adjust my scale. My y-axis is the number of apples we're producing in total. My x-axis is the number of extra trees. And so we can see when we plant no extra trees, we have 24,000 apples in total. I can see here if I planted 60 extra trees, there'd be so many trees that the idea is we'd have, according to our model, we'd have no apples because I've gone crazy planting trees and they've all kind of crowded each other out. But that's it. I can see right here, that's the peak, my maximum. And notice that confirms what we did with our derivative, that I can see here when there's 10 extra trees planted, that'll be our maximum. In this case, I can also see there's 25,000 apples we'll produce. All right, with that said, this idea of going to the graph was not essential, but we always have access to a GDC in this course. And so ideally, we can be fluid in how we want to approach this, and that's the best use of our time. All right, a different question with a little more structure. So we have someone preparing for a craft fair, needs to decide on the quantity to take to the fair. So to make each product, she needs to invest $30. So no matter what, spends $30. After this initial investment, the materials for each item cost $10. From past experience, she estimates that if she charges P dollars for each item, she will sell 100 minus 2P items at the fair. All right, so it just basically means that the more expensive the item, whoa, that is a very thick marker. Let's go a little less crazy with that. The more she charges for each item, the less items she'll sell, 100 minus 2 times the price, which makes sense. The cheaper something is, or the more expensive something is, the less you expect to sell. However, let's look at these questions kind of step by step. So the first question is determine P of N, where N represents the number of items she expects to sell. So if I look right here, we have P, this is P equals, this here, my apologies. Oh, take 3. This P we see here, that's how much she's charging. That's the same variable I have here. But all of this together tells us the number of items. So if I want to answer this first part, I can start by saying that equation there is really N equals 100 minus 2P. This is, if I know the price, I can find the number of items that we expect to sell. For part 1, I want the other way around. I want P of N. I want to basically find the inverse of this. I want to solve for P. And so I need to take this equation here and just solve for P, which pretty quickly I should get 2P equals 100 minus N, or P equals 100 minus N over 2. With that said, I'm going to write this as in 2 terms, so I'm going to divide each of these by 2, so I get 50 minus N over 2. So this here is P as a function of N. I'll write it in function notation. All right, so there's the first part done. That, if I know the number of items, this is the price that we should sell them at. All right, so next part, determine R of N, the expected revenue function. Well, revenue is a relatively simple calculation. Revenue is the price, which we have right here, times the number of items we expect to sell, which is N. And so for part 2, revenue as a function of N. Revenue in general, again, is just price times the number of units, number of items. So in this case, the price is this function right here. I'm going to go with 50 minus N over 2. And the number of items is N. So there's my revenue function, 50 minus N over 2, or 1/2 N times N. I'm going to distribute the N here, so I'll write it as 50N minus, I'll write it as 1/2 N squared. There's my revenue as a function of the number of items. All right, step 3, I want the profit function. So profit is revenue minus the costs. So profit, capital P of N, is going to be the revenue. So 50N minus 1/2 N squared. That's my revenue. Take away all the costs. And so what are the costs? Actually, I'll do it like this. We have our $30 automatically. Don't forget about no matter what, you have to invest $30. So minus 30. But also, it says up here that each item costs $10. So for every item she makes, times 10 is the cost. So the profit is going to be my revenue minus 30 minus 10N. Which I might as well simplify this, collect like terms, and I get 40N minus 1/2 N squared. So there's my profit function. Oh, minus 30. All right, another quadratic function. So now, for step 4, I want to find the derivative of this. So I'll do this right here. So the derivative of this function, so P prime of N, capital P, is just 40 minus 1/2 times 2 is 1, so minus N. And the minus 30, that's a constant. The derivative of that is 0. So there's my very nice and simple derivative. And so if I make this equal 0, then I can see N must equal 40. And so that means 40 items is how many items I should make to maximize profit. So should make or sell 40 items. That said, I also want to figure out not only how many items to produce, the maximum profit. And so I have my profit function right here. So the last step is just to take that 40 and substitute that into n. And if I do that, really I'm finding the profit at 40, P at 40. You should get a total of, 770, if I just replace those n's with 40. Which means we should, according to our model, I need to keep saying that, this is just a prediction, we should make 40 items and we expect to profit $770. Keep in mind, this question did break down, it did ask for a derivative and whatnot, and you'd probably see something like this on an assessment in IB where they want to see that you understand some aspects of the derivative. However, as well, it does say to check with your GDC, so I can check by just going to this function right here. This is what we're trying to maximize. So if I graph that, I should see a peak at 40 and 770, so let's see. Turn that off, let's graph this function. Now I gotta think about my scales here. My x-axis is the number of items, my y-axis is turn this on, there we go. The y-axis is the profit, there's my peak, and notice we have the same values that we came up with. 40, 770, 40 is the number of items, 770 maximizes the profit. So a harder question, but in the end still came back to a quadratic function, and the GDC, or my graphing device, can confirm that we're correct. All right, lastly, probably the hardest of these. What is the volume of the greatest cylinder that can fit inside a cone with a height of 8 centimeters and a base radius of 4 centimeters? So if I look at this cone here, I'm telling you this base radius from here to here, that is 4 centimeters. And this height is 8 centimeters. So that's a given. That's not a variable. All right. But everything else is a variable. The cylinder that's in here, for example, I could make a really tall, skinny cylinder. I could have a really stout, wide cylinder. But chances are something that looks more like this that was already given will have a greater volume. So what's the dimensions of it that would give us the greatest possible volume? Or really the question's asking, what is that volume? So let me look at my diagram here. And I need to pay attention to this. That's a variable, the radius of my cylinder and the height of my cylinder. Those can change. So let's get set up. So the volume of a cylinder is just area of the base times the height. So in this case, the volume of my cylinder is, area of the base is pi r squared times the height. So that's the volume of this. Right now, my volume, I want to maximize this, but I have two variables. I need to get it down to just radius or height. So I need to replace one of these variables in terms of the other. I need to really figure out the relationship between the radius and the height. So if I go back to this is where things get trickier. And for this, I'm actually going to redraw just this half of the diagram. I'm going to which is a right triangle. So if I look at my diagram here, I have a right triangle here. So let me redraw that so I can put a bit more detail into it. So I have something like this roughly. So that's the cross section of my cone. I know this is 4 centimeters. I know this is 8 centimeters. And then I have my cylinder here, which has a radius right here and a height right here of h. I'll put the h over here. So I need to see how, and keep in mind, this radius and height doesn't have to look exactly like this. It can, that point I just kind of drew can go anywhere along this line. We want to find the point that will lead to the greatest volume. So what's the relationship between the R and the H and the shape of this cone? Well, one way of approaching this is to realize that this triangle here is similar to this big triangle here. No matter how I draw my radius and my height, that smaller triangle, the one I've drawn in orange, is the same shape. It's similar to the big triangle, even if I imagine my radius being way down here. This triangle here is similar to the big triangle. That's it. It's getting exceedingly messy. So let me unmessy this a bit. But that key of realizing they're similar triangles is going to bring things together. Because that means this triangle here, which is the distance from here to here, is 8 minus h. 8 is the distance all the way from the top and the bottom. Height, h is just the distance of the cylinder. So that little part at the top is 8 minus h. And that corresponds to the total height of 8. And this radius right here of r, that corresponds to this distance of 4 here. So I can say the ratio of 8 over 4, the height of the big triangle divided by the base of the big triangle, must be proportional to the height of the smaller triangle, 8 minus h, divided by the base. Sorry, my screen keeps going weird on me. The base of my smaller triangle. So I have this. Now, this reliance on similar triangles goes back many grades. It's easy to forget, but it tends to come up in a number of calculus questions. 8 minus h. All right, so that kind of shows me the proportion again, because 8, these two sides correspond to one another, these two sides correspond to one another, which means now I can solve for either r or h. I can isolate either of these variables. If I just look at my volume function, it'd be kind of nice if that h was in terms of r, because then I could just substitute it in quite nicely. If I tried to substitute r the other way around, I'd have whatever I put in there, I'd have to square, and that's kind of annoying. So I'm going to take my equation here, I'm going to solve for h. So if I focus on this, well, first 8 over 4 is just 2, so might as well write this as 2 equals 8 minus h over r. Multiply both sides by r and divide both sides by 2. I get, actually, sorry, I want to solve for h. Multiply both sides by r, I get 2r equals 8 minus h. Solve for h, I quickly get h equals 8 minus 2r. And so that h I see right here, I can substitute with 8 minus 2r. And now the hardest part of this question is done. The hardest part, in my opinion, is figuring out the relationship between the radius and the height in this context. So now I can say, okay, the volume here will equal pi times the radius squared times 8 minus 2r. And at this point, I could go straight to my calculator and just graph this. I'm trying to maximize this function here, but let's just focus on this algebraically. I get pi times, if I multiply out the r squared here, I'm going to leave the pi because I have just a nice common factor of pi here. I get 8r squared minus 2r cubed. Okay, that's still my volume. Notice at this point, if I look at what I have right here, there's a common factor of 2r I can take out of this. Actually, no, I could do that, but I'm just going to differentiate right now. So let me differentiate this function. So v prime, that constant of pi doesn't affect things. That's kind of, constants are nice when differentiating. The derivative of this inside part would be 16r minus 6r squared. And now I want to make this derivative equal to 0, which if I take out more factors makes their life easier. This is a quadratic function, and so taking out factors is nice. I can take out a factor of 2r from all of this. So I'm going to take out a factor of 2r from all of this. Oh, what did you do? There we go. Oh, sorry. It's not letting me change. There we go. So if I take out a factor of 2r from here, I get pi times 2r, and then I get just 8 minus 3r right here. Or if I write it, I'll leave it like that. Or I can write 2 pi r. I'll be a little more conventional. Keep in mind, this is my derivative right now. And so if I want to make my derivative equal 0, I could actually see my solutions. One of my solutions is 0. One of my solutions is 8/3. So I can see r equals 0 and 8/3 from looking at my factors here. With that done, I have 2 points to look at. Well, one of them I don't need to think about. If my radius is 0, that means I don't have a cylinder, which means that's one of my minimums. So it's not a meaningless number overall, but that's a minimum volume. I'm trying to find the maximum volume, which means this must be the maximum volume. Which means when the radius is 8/3 of a centimeter, we should have our maximum volume. And so now the question does ask for what's the actual volume. So I got my radius, let's find my height. And we can see right here, height is 8 minus 2r. We now know what r is. So height equals 8 minus 2 times 8/3. 8 minus 2/3 is 8 minus 16/3. Find a common denominator and you get, what do you know, another 8/3. And so when our radius and our height are the same is when we have the maximum volume. And so now let's find that maximum volume. Let's go back to the start. I can say, therefore, the maximum volume is going to be pi times the radius, 8/3 squared, times the height, another 8/3, which is really just pi times 8/3 the power of 3, which, I'll leave this as an exact value. I get pi times 512 over 27, or a more conventional way of writing this is 512 over 27 times pi. My units are cubic centimeters. That's it. That's my exact value. If you were to find a decimal approximation, you get about 59.6 cubic centimeters. Now, I found an exact value by differentiating. Keep in mind, though, if this really was an assessment question written like this, you wouldn't actually have to differentiate. I'm not saying it'd be easy. You still have to find a way to take your volume function and write either radius in terms of height or height in terms of radius. But once you get to this stage here, you could just graph that function. So to finish off, that's what I want to do. I'm going to turn this off. Here is the function that is our volume function. Let me zoom in here a bit. And so notice there is one of my stationary points at 0, 0, but that just means when the radius is 0, my volume is 0. I know that. This is what we're really trying to find out. That's the maximum value. And I can see when my radius is 2.6 repeating, which is 8/3, my maximum volume is just shy of 60 cubic centimeters. So before I stop, just keep in mind, there's a huge variety of questions here. If we're an SL student, you're not expected to be able to do this much algebraic work. If you're an HL student, you will be expected to do. I mean, this algebraic work here is just quadratics. It's essentially pre-calculus 11 work. Doesn't mean it's easy, but it depends on, which course we're in about how far along we're expected to go from a purely algebraic standpoint.